So today we are going to start our brief introduction to filter circuits. So let me ask you guys a fairly simple question, I think. Do you have any idea what a filter in general does? Not even worried about electrical filters, but just filters in general.
Do they kind of get rid of the stuff you don't want?
Exactly right. That is a perfect description. So like the air filter in your car's intake system gets rid of the dust particles in the air and prevents them from getting into your engine and contaminating your gasoline and stuff like that. Well, an electrical filter does much the same thing. It suppresses or rejects unwanted portions of a signal. So there are 4 different types of signals that, or excuse me, of filters that we'll deal with in this class. And I'm going to describe them graphically at first. And we'll talk about the ideal filter response. And then we'll talk about the practical or real filter response. So let's say this first one is going to be a function of omega. They're actually all going to be functions of omega. And I'm going to look specifically at the magnitude of the transfer function, where the transfer function h of omega will be something that we discuss in a little bit. So our first filter circuit that we're going to talk about is going to behave something like this, where we have some amplitude, and because we're going to be dealing with passive filters, the maximum amplitude will usually be 1, shouldn't be higher than 1 for sure. And at a particular frequency, which I'm going to call omega c, the cutoff frequency, the amplitude of your signal drops to 0. So we have a pass band for all frequencies below omega c, and we have what's called a stop band at all frequencies above omega c. This type of filter is what's called a low pass filter. Now this is the ideal behavior of a low pass filter, where we would see an abrupt shift between the pass band and the stop band, meaning that everything beyond omega c gets completely attenuated. In practice, we'll have something that's a bit smoother. So instead of being that abrupt shift, it'll be something like this. Where the steepness of that transition between where it's at 1 and where it's at 0 is due to the order of the filter. So in this class, we're going to be looking only at first and second order filters. So we're going to see that that steepness is actually pretty broad. So it's going to take a bit of, it's going to have a large frequency range in order for the filter to be considered completely attenuating the signal. Our next filter of interest is going to look something like this. So it is effectively the opposite of a low pass filter. Above a cutoff frequency of omega C, we have our pass band. Below omega C, we have our stop band. And this guy is what's called a ideal high pass filter. So everything above a particular frequency does not get attenuated. Everything below that cutoff frequency does. We'll see that a practical high pass filter has effectively a similar response. It's going to start off low and then increase like so. So there's still a actual range of frequencies it takes for the filtering to occur. Our next filter of interest is going to have a response that looks like this. So we have a frequency here, I'm going to call omega low, a frequency here, omega high, and directly in the middle, a frequency omega naught. And that omega naught there is actually pretty much exactly the same omega naught that we were dealing with in our RLC circuits. Okay, so it's the resonant frequency of the system. So we have a stop band that ranges from, a pass band that ranges from omega low to omega high. And then we have two distinct stop bands. Like so. So this guy is what's called a band pass filter. Because it passes all frequencies in the frequency band of omega low to omega high. That's maximum amplitude 1 for a passive filter. And for a practical one, it's going to look like a combination of the response of the low pass filter and the high pass filter. So something like this. And then our fourth and final generic filter type will be the opposite of a bandpass filter. So we still have omega low, omega naught, and omega high, but now we have two discrete pass bands stop band in the middle. And so this guy is what's called a band stop filter. A practical realization will have a response that looks something like this. It'll zero out at omega naught, then rise like so. So all of these filters are a form of signal processing, okay? So much like our op-amp circuits were used for signal processing, and as much as we were able to add, subtract, differentiate, and integrate signals, these process not by doing mathematical functions, but by rejecting specific frequencies. So for those of you that have had Math 245 and are aware that any signal can be broken down into a sum of sinusoidal signals having different frequencies due to what's called a Fourier transform, we can easily see how filters can accept or reject specific sinusoidal components of a signal. Pardon? You didn't learn Fourier analysis in 245? Oh, well, crap. Well, you will learn later in your EE career then that you can break any periodic or aperiodic signal into sinusoids. Yeah, you'll actually learn that. I'm really surprised you didn't cover it in 245. Okay. Well, I feel like your 245 teacher did you guys a disservice. So you'll learn about Fourier analysis then in ELEN 321. So that will be the winter of your junior year. So I guess for now, you'll just have to take it on faith that we can break any signal into sinusoidal components. So because we can break any signal into sinusoidal components, we can actually employ steady state sinusoidal analysis techniques to kind of figure out what filters are doing. So let's say that we have the following circuit, all right? So I'm going to have simply a resistor with some value R and a capacitor with some value C, like so. And I apply a time domain signal, Vn of t, at the left-hand side or the input, and I measure a time domain signal, V out of t, on the right-hand side or the output. In the frequency domain, this circuit looks like this. So we're going to have an R here, but we'll have a J omega C, excuse me, 1 over J omega C. Oh my gosh, can't believe I screwed that up. Here. And we would have some phasor input, Vn, whose value depends on the frequency, and measure some phasor output signal, V out. The transfer function of this particular circuit, H of omega, is defined to be the ratio of V out divided by Vn. So the transfer function for this circuit is very similar to the gain equation for our op amps, but we have some implicit frequency dependence here. So in a moment, mathematically, we're going to describe exactly what's going on here, but we can actually kind of qualitatively look at this guy and figure out what's happening, right? So if we were to apply some sinusoidally varying voltage source, Vs phasor, to the input side of this guy, what would our output generically be? Like what kind of circuit is this? Let's start there. Well, I mean, it's an AC circuit, but it's a specific type of AC circuit. So if I had a DC source and then two resistors, and I was trying to get the voltage drop over one of those resistors, I would consider this to be a voltage divider circuit, right? And that's exactly what this thing is. It's a voltage divider circuit whose output depends on the frequency of excitation because the impedance of the capacitor depends on the frequency of excitation. So at very low frequencies, what does the capacitor look like? An open circuit, exactly right. And so for very low frequencies, we should see that V out is exactly equal to V in because effectively no current's flowing anywhere. And so the input signal gets completely passed to the output. But at very high frequencies, what does the capacitor look like? A short circuit, exactly right. So as omega gets larger, 1 over omega gets closer and closer to 0, right? So it would look like a short circuit, which means that our output signal would go down to 0 volts. So this guy is a low pass filter because it passes very low frequencies and attenuates very high frequencies. So let's mathematically describe what's going on here. All right. So what I like to do explicitly here is treat by input voltage as simply a 1 angle 0 volt phasor, okay? Mathematically, it'll make a lot of sense in just a moment why we're doing this, but 1 angle 0 works because it doesn't matter what the frequency is, right? So 1 angle 0 would be representative of a 1 cosine 2t plus 0 degrees sinusoid or 1 cosine 845t plus 0 degrees sinusoid. So this is a simple 1 angle 0 for all relevant frequencies. So our transfer function, h of omega, in this case, would be 1 angle 0 degrees multiplied by 1 over j omega c divided by r plus 1 over j omega c. That's our output voltage, V out, as a function of frequency. And then we would divide by V in, which is 1 angle 0 degrees volts. We can see easily that that 1 angle 0 degrees cancels each other out. So looking at this guy as a voltage divider circuit actually makes determining the transfer function trivial because it's just the resistor ratio or the impedance ratio portion of that voltage divider equation. So I'm going to rewrite it as 1 over j omega c divided by r plus j omega c. And then I'm going to multiply this guy by a factor of j omega c, excuse me, that should be 1 over j omega c, like so, just because I don't like having fractions in my numerator and denominator. And what I'm left with is 1 over 1 plus j omega rc. So this is my transfer function, okay? Now, if we were to try to plot this, we would have some difficulty because there's complex numbers involved, right? So instead, we're going to break our transfer function down into two portions, a magnitude portion and a phase angle portion, so that we can see what's called the frequency response the magnitude of h of omega and the phase response. Theta h, and it's how the phase angle changes with frequency. All right, so to determine the magnitude, we need to first break down h of omega into a rectangular complex number, right? And so what I mean by that is right now we have a rectangular complex number in our denominator, but I want to have a rectangular complex number in the numerator with a real number in the denominator so that we can easily break it up into real and imaginary portions, right? So if I start with this 1 over 1 plus j omega RC bit, how can I break this thing up easily? We've done it before. Yeah, so I multiply this number by the complex conjugate of the denominator divided by the complex conjugate of the denominator. So that would look like, let me put a bracket around this, 1 minus j omega RC over 1 minus j omega RC, which would leave me with 1 minus j omega RC over 1 squared. So 1 plus omega RC quantity squared. And then I can break this up as 1 over 1 plus omega RC quantity squared minus j omega RC over 1 plus omega RC quantity squared. So now I have an easily discernible real and imaginary part of my transfer function. So my frequency response, the magnitude of h of omega is simply going to be the square root of the real part squared. So it's going to be 1 over 1 plus omega RC quantity squared plus the imaginary part squared. So that's going to look like negative omega RC divided by 1 plus omega RC quantity squared. So when I square these two functions, or these two components, I'm going to get a common denominator, right? So I'm going to have 1 plus omega RC quantity squared, right? And then in my numerator, I'm going to have 1 squared, which is 1, plus negative omega RC, that quantity squared. So it's just going to look like 1 plus omega RC squared, like so. Obviously, this guy is going to cancel that out. right? So I have the same thing. My numerator is one value, my denominator is that value squared, so I can get rid of that squared sign. And what I'm left with is 1 over the square root of 1 plus omega RC squared. Okay. So we can do a couple of things here to check some stuff out. All right. The first thing that we can do, let's figure out what the amplitude is when omega is equal to 0. Any thoughts? So we literally just substitute in 0 for omega into our expression, and that leaves us with 1 divided by the square root of 1, which is 1. When omega approaches infinity, what happens? We have 1 over effectively the square root of infinity, which is going to be infinity. So it goes to 0. So mathematically, we understand now why this is a low pass filter, right? At very low frequencies, all of the signal is passed through. At very high frequencies, none of the signal is passed through. Now, we can also look at this guy and figure out what the cutoff frequency is. So our cutoff frequency for real practical filters is defined to be the frequency at which half of the signal power is attenuated. We define this numerically in 2 different ways that represent the exact same thing, okay? So one way that we do this, we call it the 3 dB frequency. So that means that our signal has decreased by a value of 3 decibels, which I totally understand that you guys might not exactly know what decibels are just yet. A decibel, mathematically, we would have (10 log) output power divided by the input power gives us our decibel value. Well, this is going to be the exact same thing as 20 log V out over V in. Okay, so that's how we find the decibel value. Our other means is just simply saying that the magnitude of h of omega is exactly equal to 1 over the square root of 2. They represent the exact same point. It's just from 2 different perspectives. One looking at the magnitude as just a number, and then the other one looking at the magnitude as a decibel number, where decibels is just a unit used in frequency analysis fairly regularly. All right. So to me, figuring out what value of omega makes the amplitude equal to 1 over the square root of 2 is fairly straightforward here, right? So Any thoughts on what that might be? So we already have a 1 in the numerator, and we already have a square root sign in the denominator. So we're pretty close to halfway there already, right? So I could argue that, so we want 1 over 1 plus omega RC squared to be equal to 1 over the square root of 2, which implies that 1 plus omega RC squared has to equal the square root of 2. So if we squared both sides, we'd have 1 plus omega RC squared is equal to 2, or omega RC squared is equal to 1. From this, omega is just going to be, so that is our 3 decibel or half power frequency. So it's related to, effectively, it looks like almost a time constant, right, for a circuit like this. Yeah. All right. So there's our cutoff frequency. Nothing wild or crazy there. Now let's look at our phase response. So theta h as a function of omega is going to be the inverse tangent of the imaginary portion, which is negative omega RC divided by, 1 plus omega RC quantity squared divided by the real part, which is just 1 over 1 plus omega RC quantity squared. So these denominators cancel each other out. So we're going to have the inverse tangent of negative omega RC, which is the same as the negative inverse tangent of positive omega RC. So let me get my mouse real quick, and I want to play around with LT Spice. Looks like I left my calculator in my office. It won't be a big deal. All right. So remember what, there we go. I get some of this crap on my desktop. Get rid of that. Open LT Spice. There we go. So if I wanted to draw my filter circuit, I would literally just put my resistor in series with my capacitor. If I can get this zoom crap out of the way, let's just move it down here for now. That is not a capacitor. And let's see. So like this. So I'm going to choose my ground point down here at the bottom because if I'm using LT Spice, again, I have to have a ground. And what I'm going to do now is I'm going to put in a voltage source. Like so. And I'm going to put in my voltage. So to do this, I'm going to go into the advanced tab and I'm not going to do anything whatsoever with the left-hand side here, okay? So we are going to be doing what's called small signal AC analysis. So I'm just going to put my AC amplitude to be 1 and my AC phase to be 0. So I'm forcing my input voltage to be a phasor of 1 angle 0 degrees. All right. I'm going to give myself a resistor value. Let's just do something kind of simple. Have a resistor value of 1 and a capacitor value of 1. And I'm going to label this terminal right here as V out because that will be my output voltage with respect to ground, which is what I'm measuring. And that's also going to be representative of my transfer function because I'm using a 1 angle 0 source. So when I run the simulation, I need to now set it to AC analysis, okay? So I'm going to do a decade sweep. The number of points per decade, I'm going to put it to be 1,000. I might have to change that. And I'm going to start it at 1 millihertz, so 1 lowercase m, and I'm going to end it at 1 kilohertz. Okay. So when I look at my output, hopefully you guys on Zoom can see this, I get 2 graphs. All right. The solid line is my frequency response or the amplitude, how it varies with frequency. And the dotted line is my phase response. All right. So notice here that my left-hand side scale is in decibels. All right. So if I wanted to figure out what the corner frequency of this guy is, I would click here. And then I just drag this cursor until the magnitude is -3 decibels. So that's pretty close. So it says that I'm getting a frequency of 158.547 millihertz. Based on our R and C values, we would expect the corner frequency to be 1. But it's 1 radian per second because we calculated omega. We would need to divide that by 2 pi to get our linear corner frequency. All right? So we got to pay attention to stuff like that. So if you calculate the corner frequency in radians per seconds, LT Spice is going to give it to you in linear frequency. So there's going to be a 1/2 pi factor that you're off. So our mathematical description is actually describing this extraordinarily well, right? I don't even know how to use your calculator, so it doesn't, it's okay though. So this is another place where LT Spice operating in, everything in degrees effectively in linear frequencies is going to make it slightly different than our analysis where we're used to working, in angular frequencies involving radians and all that kind of stuff. But it's all the same. It's just looking at it from a slightly different perspective. So we can easily see this is what it looks like. We have a magnitude where for very low frequencies, our magnitude of 0 dB corresponds to a magnitude of 1, right? Because 20 log of 1 over 1 is, so 20 log of 1 is going to be 0, right? Because anything to the 10 to the 0th power is what gives us 1. So we have 0 dBs for very, very low frequencies. And then once we get, let's see. So once we get to 158 millihertz, we're down to -3 dB. So we're at half of our signal power. And then once we get down to roughly -60 dBs, that is engineering for 0. Yeah, there's my cursor. Oops, that's not what I wanted to do. And be easier to just run the simulation again than try to fix that. So what I'm trying to find, there's my cursor, where we get to -60. Here we go. So at about 165 hertz, we get to -60 dB. -60 dB means that our signal has 1,000 times less signal power than it started with. So that's why we consider that effectively 0. So like if you ever happen to go work for a government facility or anything like that, designing this kind of stuff, like designing electromagnetic shielding or anything like that, that's what they're looking for usually is a 60 decibels of attenuation as a minimum, because that means that whatever you put in, less than 1,000 comes out, right? So that's how you design things to guard against electromagnetic interference and EMPs and all that kind of good stuff. 60 dBs is kind of the benchmark. Anything you can do over that is fantastic. But once you get to around 120 decibels, which means your signal power is 1,000,000 times smaller, past that, all your numbers are effectively garbage because you can't really measure beyond that threshold. Pardon?
Why don't they just use lead coding? Does it calculate all this?
So lead coating can work in some instances, but how expensive do you think it would be to ship a container made of lead from here to Afghanistan? Prohibitive, right? It would take a very, very large plane, a whole lot of fuel to do it. So typically speaking, the military is looking for lower weight applications than just putting a lead shield. Yeah, like making it efficient to transport. A research project that I'm loosely involved with right now is developing effectively field erectable electromagnetic shielding enclosures that could be destroyed very easily with the intent of, we bring them there, we bring them to a foreign land, we use them, and then we destroy them so that they can't be used by our adversaries. A lot of my PhD research was in electromagnetic shielding and all that kind of stuff. So, all right, so this is a low pass filter. What I'd like to do now, 30 minutes or so, is change some things up. So let's look at what happens if our circuit of interest swaps the positions of the capacitor and the resistor. And we'll work it starting off in the frequency domain. Where here's our input. Here's our output. So all of these filters that we're going to be dealing with in this class are all going to be series combinations of resistors, capacitors, and inductors. A question that I was asked previously is, why is it never a parallel combination? Well, if you had a parallel combination, the output and the input would always be the exact same thing because the voltage sources would be in parallel. So just in case that popped into your head, there's a pretty simple explanation as to why it's always in series. It has to be to work as a filter. So our transfer function for this guy, h of omega, is simply going to be R divided by R plus 1 over j omega c. We can multiply by j omega c over j omega c, yielding j omega rc divided by 1 plus j omega rc. And if we multiply this guy by 1 minus j omega rc over 1 minus j omega rc, we'll then break it down into its constituent real and imaginary parts from which we can find our magnitude response and our phase response. So I'm going to have, let's see, so j omega rc times negative j omega rc is going to look like omega rc quantity squared. Plus j omega rc, so that's my numerator. And my denominator is going to be 1 plus omega rc quantity squared. Hopefully that complex math was fairly straightforward to follow. From this, h of omega magnitude, excuse me, will be the square root of the real part squared. So that's omega rc quantity squared divided by 1 plus omega rc quantity squared, that whole fraction squared, plus omega rc divided by 1 plus omega rc quantity squared, that whole fraction squared. And now I'm going to have omega rc squared times 1 plus omega rc squared. So what I've done here, obviously I'm going to have omega rc to the 4th power for my left-hand contribution, and then omega rc squared for the imaginary part contribution, and I've just factored out omega RC squared from that omega RC squared plus omega RC to the fourth power. This will be divided by 1 plus omega RC quantity squared. And so this portion of the numerator cancels out one of the powers of the denominator, leaving me with omega RC divided by 1 plus omega RC squared square root. So we can do the same thing. The magnitude of our transfer function at omega is equal to 0 is now going to look like 0 over the square root of 1, which is 0. The magnitude of our response at omega is equal to infinity is going to look like infinity over the square root of infinity squared, which is just going to be 1. And so we see that we have a high pass filter, right? Because it attenuates all of the low frequencies and passes extremely high frequencies, right? Our corner frequency is going to wind up being the exact same thing as it was before because we only have a resistor and a capacitor, so it really can't be anything else. If we look at our phase response, theta H as a function of omega, this is going to be the inverse tangent of the imaginary portion. So that's going to be omega RC divided by 1 plus omega RC squared divided by the real portion, which is omega RC squared divided by 1 plus omega RC quantity squared. Our denominators cancel each other out, and we get the inverse tangent of 1 over omega RC. So that's how this RC pass filter behaves. Now let's look at what happens when we throw an inductor into the mix. Here's our input side. Here's our output. What should our transfer function be? Are we taking the voltage drop over the resistor? So it shouldn't be R over anything, right? Because we're just doing simple voltage division. So it's going to be the impedance that we're taking the voltage drop over, J omega L, divided by the series impedance seen by the input signal, R plus J omega L. Now in this case, we don't have to multiply by any things to clear fractions. So we're going to multiply by R minus J omega L. And so that's going to give me omega L squared minus J omega L R divided by R squared plus omega L squared. And breaking this guy down, I'm going to have omega L squared over R squared plus omega L squared minus J omega L R over r squared plus omega L quantity squared. Let me make sure I did my algebra here correctly. So j times a negative j gives me positive 1, so that's where that comes from, and then I have j omega LR. Actually, that should be positive, because j omega L times R should just be positive j omega LR. Yeah, okay. In the grand scheme of things, that wouldn't have made any bit of difference whatsoever, because we wind up squaring and square rooting everything and getting rid of all those signs, but it doesn't hurt to be correct from the get-go. Our magnitude response is then the real part, so omega L quantity squared divided by r squared plus omega L quantity squared. And we do our imaginary part, which is omega L R over r squared plus omega L squared, square the whole thing, square root. And when I square the imaginary part there, I'm going to have an r squared times omega L squared. And then I have an omega L squared squared. So if I factor out that common factor of omega L squared, I get this in my numerator. And I have r squared plus omega L squared quantity squared. So this guy in the numerator cancels out one of my powers in the denominator, and I'm left with omega L divided by r squared plus omega L quantity squared. Oh, and square root this guy. My magnitude, when omega is equal to 0, is going to look like 0 over the square root of r squared. So that's going to be 0 over some finite value. So it's going to be 0. The magnitude when omega goes to infinity is going to look like infinity over the square root of infinity squared, which is just going to look like 1. So in this particular configuration, we get a high pass filter. Does that make sense? We can actually determine that just by looking at how the impedance of the inductor behaves, right? So when the inductor is at very low frequencies, it looks like a short circuit, which is why it's attenuating everything. And at very high frequencies, it looks like an open circuit, which is why it's passing everything. So again, we can really get some kind of qualitative understanding just by how these filters works, just by understanding how the impedance of our component behaves as frequency changes.
So filters, are these what you use for like radar absorbing coding? Isn't that our radar signals basically? Is it popular to have the sound important?
Yeah, no. So these type of circuit-based filters are used a lot in telephony and radios and all that kind of stuff. Now you're talking, so radar absorptive coating and stuff like that is more of a mechanical or material filter, yeah. So that's effectively using what are called waveguides. And waveguides are absolutely designed by electrical engineers, but they use effectively what's called transmission line theory to figure out how they behave. So it's specific shapes that can reject or pass specific portions of the electromagnetic spectrum when your signal is traveling through a medium like air, as opposed to traveling along a wire like what we have here. So it's the same basic principle, but it's implemented in a different way. Yeah. So waveguides is all about like the size and the shape of an aperture, which is just the size of the hole that lets the signal pass through, right? So if you have very, very tiny holes, it's going to reject a bunch of low frequency things, and it's only going to pass things through where the wavelength of the signal is 4 times as long as the diameter of the hole. I think that's how it's been a hot minute since I had to do that kind of stuff. So it's the wavelength is related to the size of the aperture, and I think it's a wavelength over 4 relationship. And then you can get in interesting things like, so later on in your career and a little bit here at Tech, you'll learn about things so where you can like have a signal pass through a cable and then it'll go through a horn kind of thing to convert that signal traveling along the wire to a electromagnetic wave as well. And then you feed that into a waveguide. So there's like these connections between we're passing it along a wire versus we're passing it through free space or some other type of medium.
Do you use channel as all the stuff that's normal?
Yeah, I mean, like spectrum analyzers, all that kind of good stuff. Yeah, because even like these metallic, the waveguides, typically speaking, have some sort of metallic surfaces and all that kind of stuff too. Like you're capable of observing signals and all that kind of stuff on them. But then you also get into problems called, let's see, the skin effect and all that kind of good stuff, to where you have to be careful about the size of the conductors that you use, because at very high frequencies, so like in a DC circuit, oh, we got time, okay. So in a DC circuit, all of the current that passes through the conductor uniformly distributes through the cross-section of the conductor. So there is a uniform current density flowing through all parts of the wire. Well, as the frequency increases, you'll find that the current gets more and more concentrated towards the outside or the surface of the wire. Exactly. So there's almost no current flowing through the center of the wire, and almost all of the current winds up flowing around the outside surface. And the higher the frequency gets, the more and more of the current flows only on the surface of the wire. So that's another place where waveguides and all that kind of stuff come into effect, because what's happening in the middle is completely unimportant because it carries no portion of the signal. Mm-hmm. In your E&M classes. So starting later on this year, you'll start learning about all this kind of good stuff. E&M classes are my favorite classes to teach, and I haven't actually been able to do it since I got hired as a full-time professor. When I was a grad student, I taught the E&M classes for like, I think 4 or 5 years. I love that stuff. That's what all my PhD dissertation was on, was E&M. So, all right, so so to determine our corner frequency, we need omega L over the square root of r squared plus omega L squared to be equal to 1 over root 2. So let's see, how are we going to make, I know what the answer is supposed to be. I want to get there mathematically. So we could have omega L quantity squared over R squared plus omega L quantity squared is equal to 1/2. So that would give us R squared plus omega L squared is equal to twice omega L quantity squared, or R squared is equal to omega L quantity squared. Omega squared, L squared. So that would be omega C is equal to R over L. I think I made a mistake previously, actually. Sorry. I think I got lazy with my math here, and I should not have a square root sign. Yeah, no square root there. And it's because I was forgetting that I was going to have omega squared when I square that term. Yeah, so there shouldn't be a square root there. All right, my apologies. So again, we see that it's just the inverse of the time constant for an RL circuit, which makes sense. All right, for our phase response, we're going to have the inverse tangent of the imaginary part, which is omega LR over R squared plus omega L quantity squared divided by omega L squared over R squared plus omega L squared. So our denominators cancel each other out, and then we're going to have an LR cancel out one of these powers such that we get the inverse tangent of R over omega L. So we're running out of time. What do you think is going to happen when we change the position of the inductor and the resistor? So if we change the position, let's not get into this in too much detail, but we put the inductor here, having an impedance of j omega L. We put the resistor here. And we're effectively looking for the voltage drop across that resistor, right? So yes, so at very high frequencies, at very low frequencies, the inductor is a short. At very high frequencies, is an open circuit, right? So at low frequencies, the inductor looks like a short, and so our input voltage is just in parallel with that resistor over which we're taking our output, right? So at low frequencies, we pass signals, and at high frequencies, it opens up and none of the signal gets passed through. So this is a low pass filter. We can analyze it using the techniques that we just did. But since we're out of time effectively, I think I'm going to make you do that for homework. Not wildly difficult or anything like that. So what we talked about today were the different combinations of first order practical filter circuits. So RC filter circuits and RL filter circuits. In order to get the band pass and stop band behavior, we're going to have both a capacitor and an inductor in the circuit simultaneously. Because effectively what we're doing is we're relying on the inductor to provide some portion, either the low pass or the high pass portion, and the capacitor to give us the other.
So
Right.
the block ones are the second order ones?
Let me scroll up here, okay? Way back to the beginning. So we talked about the low pass and the high pass, where it's simply we have one stop band and one pass band. Those can be recognized by first order and higher filter circuits.
Those are second order.
Right. For the band passed and band stop filters requires second order and higher, right? So we can actually make low pass and high pass filters out of RLC circuits very easily. But we can also get band pass and band stop, right? In circuits 3, you're going to learn about things like Chevy-Chev filters and stuff like that. Those are just higher order versions of what we're talking about in this class, right? We are stopping at second order filters because we stopped at second order transient analysis. In order to analyze those higher order filters, it's going to be helpful for you guys to know Laplace transform, which you do because you've had Math 245, but not all of the students going in have had it yet, which is why we can't talk about it here. Circuit 3, you're supposed to be taking Math 245 at the same time, so that all this crazy math will make sense.
Kind of looks like a unit step.
That is very similar to how it's trying to behave just as a function of frequency. Yeah. So unit step where it's 0 until it's 1 and then it's 1 in perpetuity is exactly what this thing is. Yeah.
You can cascade those?
Yes.
Just like linearly?
Mhm. Yeah, you can chain them together to do whatever you would want, which is effectively what you'll see the second order filters are, because the second order filters are still just series RLC circuits.
Yeah. So wait, would that be two eyes or? Oh no, you're being the same.
I'm sorry, I didn't.
Nothing. I was just, if you change those, then you just have two eyes, right?
Yeah, so if you chained them together, so let's say that you had a resistor and a capacitor, and then another resistor and another capacitor, like so. I'm trying to remember if you would put another resistor here, but this would be a Chevy-Chev filter, where it's just that structure chained together. And that would be a low pass. And then if you flip the position of the resistors and capacitors, you get a Chevy-Chev high pass. So what winds up happening when you create filters that way is it makes that response, that transition from low pass, or the transition from the pass band to the stop band, steeper and steeper and steeper, the more circuit elements you put in. But the elements themselves need to be matched, meaning that all the resistors need to be the same value and all the capacitors need to be the same value. Otherwise, you distort the system.
Couldn't they replace op-amps? Like, why do we need op-amps if we have, like, they're smaller?
Okay, so that's a fantastic question. So these guys, right, so there are filters that include op amps. Those are called active filters. These passive filters, they just reject some portion of the frequency. They require no external power whatsoever. The limitation is that they provide no amplification either.
Oh, right.
Right. Yeah, but when you do them with op amps, you get these filters and you also get amplification. And what's interesting is that an op amp high pass filter is an integrator and an op amp low pass filter is a differentiator. Like it's literally the exact same circuit that we've been dealing with. It's just when we look at it from a frequency perspective, it does X. And when we look at it in a time domain perspective, it does a different mathematical function, but they're identical circuits. Yeah, and You'll learn all about all that kind of crap later on too. Yeah. Yes. All right. I will catch you guys on whatever the next Monday.